Hey folks, in this lesson I'm going to talk about some of the theory behind hydronium ion concentration and the relationship with pH and the pH scale, and eventually we'll get into some of the calculations for hydronium ion concentration and for pH as well. But I'll start by taking a look at different compounds and when you do mix them with water. So let's start by having here what happens when you take different salts and mix them in with water. So most common salt, sodium chloride, NaCl. So if you take that, table salt, mix it in a glass of water, what you have on the product side is, it's not a chemical reaction. All we have is the salt that dissolves. It splits apart into the ions, sodium ions, chloride ions that are now floating around in that glass of water. And it is because we do have these different ions that it does also conduct electricity. If we were to take a molecular compound, something like carbon tetrachloride, do the same thing, dissolve it in water. In this case, again, there's no chemical reaction that takes place, so the carbon tetrachloride might dissolve in the water, but it doesn't actually form ions. So all we have is, well, still carbon tetrachloride that is floating around in this liquid solution. So because there are no ions, this one here will then not conduct electricity, unlike the previous one that does conduct electricity. So in the case of acids, in fact acids and bases, they do something sort of similar to this ionic compound because they act as ionic compounds. So in its simplest form, something like hydrochloric acid dissolved in water will form the ions H+, Cl-, in the H2O, and because of that it will conduct electricity. And of course we also talked about this previously, that in fact those protons are donated over to water to form the hydronium ions. And with common base, sodium hydroxide, mixing that with water, again in this case what we're going to get on the product side is some ions, sodium ions, the hydroxide ions dissolved in the water. So again, just like the sodium chloride, this one's going to conduct electricity, and this one's going to conduct electricity. The only ones that don't are going to be our molecular compounds that are not conducting electricity. So what about water itself? What about if we just have pure water? Do we have ions that are actually formed? Well, if it is tap water, there will be ions in it. There will be sodium ions, chloride ions, carbonate ions that will conduct electricity. But if it is pure distilled water, we tend to think that there are no ions that are dissolved in it. But in fact, what does happen is we do have what is referred to as the dissociation, and we do have some of the water molecules that are essentially splitting apart. Well, in reality, what we have, if I draw this a little bit different, HOH, water, with other HOH, water molecules, and water again can act as both an acid and a base. So some of these water molecules will be acting as an acid, some of them will be acting as a base. So we can take this proton here, donate it over to the other one. So in a pure water solution, distilled water, we in fact do have some hydronium ions and some hydroxide ions. But as we'll see, it is a very, very low amount, and that is why this is actually not going to conduct electricity. Yes, we can say that there are some ions, but there are so few of these that it will not be a conductive solution that we do have. So this dissociation of the water, it is in equilibrium, and for every water molecule that does donate the protons to another water molecule, we're going to have the reverse reaction that's taking place as well. So if we take a look at the combined hydronium and hydroxide ions, multiply them together, it is like an incredibly small number of 1 × 10⁻14. So the concentration, in fact, of pure distilled water of hydronium ions is 10⁻⁷ down here, 1 × 10⁻⁷. The concentration of this is 10⁻⁷. And that's why when you multiply those together, just add together the exponents, and that gives us the -14. Okay, so the concentration of distilled water, concentration of both the hydronium ions and the hydroxide ions is this 10 to the negative 7. So that's going to be kind of significant in a couple of slides here. But let's take a look at an acid solution. So in this case here, what we do have in the example is hydrobromic acid, or HBr. So this is kind of simplified. Just a reminder again that we have the AQ indicating that it's an acid. We do have the hydrogen indicating that it could be an acid. So truly what would be happening, of course, is that we would have this in a water solution and we would be donating the protons. But just to simplify it, rather than hydronium, I just have the protons and the bromide, which would show that we do have the ions, and in fact it would conduct electricity. But because we have these forming, and because it's donated to water, we form the hydronium. This means that it is going to be an acidic solution, and so this is going to in fact be dropping the pH of that solution. The more of these that are formed, the more hydronium, the lower the pH is going to be, the more acidic that solution is going to be. So it's all really determined by the donation of the protons, how many protons are donated, and how much hydronium ion is going to be forming. So the pH scale, we see the pH scale, the basic range of the pH scale going from 0 to 14, 7 being neutral on the pH scale. So the pH scale is based upon the concentration of hydronium ions in a water solution. So if we have more hydronium ions, we're going to have a lower pH again. If we have fewer hydronium ions, then we're going to have a higher pH. So this is the actual definition of the pH scale. It is the negative logarithm of the hydronium ion concentration. So kind of wordy, it actually makes more sense if we just take a look at the equation. The pH, that number that we come up with, is the negative log, square brackets, again they mean concentration, and inside of the square brackets it is the hydronium ion. Okay, so I'm going to put it in here and we'll come back to this a little bit later. If we do have a strong acid, whatever the concentration is of that strong acid, if for example it is 0.25 moles per liter, that's the concentration of the acid. We also say that that is the concentration of the hydronium ions, okay? So they are the same. That is the case for a strong acid. That is not the case if it is a weak acid. But let's go back to the water. So for pure water, we said that the hydronium ion concentration is this, 1 times 10 to the negative 7, or simply if this is a 1, it's just 10 to the negative 7 moles per liter. Again, this is a really, really small number, right? This is what the number is, 0.0000001. That is 1 times 10 to the negative 7. So if we plug that number into this equation, so using your calculator, negative first, hit the log button, open up some brackets, and put in, you don't even have to put the 1 in here because it is just 1, 10 to the negative 7, close the brackets and press enter. And then what you end up with is, well, 7, a neutral pH. And that's exactly, of course, what we would expect for pure water. But again, where does this number come from, the pH of 7? It comes from the hydronium ion concentration, 10 to the negative 7. So anything that makes this number bigger is going to drop the pH. Anything that makes this number smaller is going to increase the pH. And we'll see some examples, of course, of that in a few slides here. So let's say that we do take this many moles of hydrochloric acid and put it in a liter of solution. So hydrochloric acid is a strong acid. So the concentration of hydrochloric acid is going to equal the hydronium ion concentration as well. Okay, they will be the same. And again, we'll come back and talk about how we know that this is in fact a strong acid. So we have 1 times 10 to the negative 4. Again, if this is a 1, you can plug it into your calculator, but it really is just the 10 to the negative 4 that we are concerned about. So this is the formula that is in your data booklet. Negative log of the hydronium ion concentration And if it is, again, a strong acid, you can just plug that number right in there. So when you are putting this into your calculator, if it is a TI calculator, this is the one that you want to hit first of all. That's the negative. Log button is along the left-hand side. You want to hit the log. And then probably more than likely, you'll get some brackets that come up right away. The general rule is if you do have a bracket that opens up, at the end you need to close it with however many brackets. So you can put in the 1.00 times 10 to the negative 4. And I think, again, there are some brackets that open up here. So we have 2 brackets that have opened up, which means at the end we need to close it with 2 brackets as well. Then you press enter, and what you come up with is, well, this number 4. So there's a little bit of a pattern that we can see here. So something that is 1 times 10 to the negative 7 gives us a pH of 7. Something that is 1 times 10 to the negative 4 gives us a pH of, let me just fix this here. I don't know if that's a 7 that I wrote or a 4, but let me go back. It should be a 7. 7. 10 to the negative 4 has a pH of 4. Something that is 1 times 10 to the negative 2 has a pH of 2. Something that is 10 to the negative 11 has a pH of 11. That's when it's always 1 times. So what if the number is something like 3.7 times 10 to the negative 11? Well, this here is a little bit bigger for the hydronium ion concentration, which means it's actually not going to be bang on 11. It's going to be a little bit less than 11. Okay, but you can go by this number here when you do your calculations. So any number that's 10 to the negative 7, it should give you a pH between 6 and 7. If you're getting something other than that, you did something wrong with your calculations. Whatever number you have here times 10 to the negative 2, it'll be really close to 2. It'll be somewhere between 1 and 2. So use that to make an estimate and make sure that you're on the right track with your calculations. What about with bases? We generally don't do calculations for the hydroxide ions in Science 30, but if you do have a base, like the sodium hydroxide, remember that it is an ionic compound, so it is going to dissociate into the ions. We, of course, would have water here as well, and water on the other side, but the point is that we're going to have, instead of hydronium, we're going to have hydroxide. So instead of the pH going down, the pH is going to go up. And instead of becoming acidic, it's going to become more basic or more alkaline. And again, look for a base, being where you do have a metal. So here I have sodium. It could be magnesium. It could be potassium. The ions here combining with them. It could be calcium. So any of those, combining them with OH, then that does result in it being a base. Some other ones as well to kind of look for, even if it's just something like MgO, magnesium oxide, that one also is going to be a base. So metals also with an oxygen, that's kind of a good indication that it's going to be a base, and you would end up having a pH greater than 7. So what about calculating the concentration now of the hydronium ions? So if we're given the concentration, if we're given the pH, we can calculate the hydronium ion concentration, or if we're given the concentration, we can calculate the pH. So in this case here, calculating the pH is the negative log, as we saw, of the hydronium ion concentration. If we want to calculate hydronium ion concentration, we need to rearrange this equation. This is kind of a weird one to rearrange. So now we want to get hydronium ion concentration isolated on its own. Everything else goes over to the other side. So it's referred to as the anti-log, but you will not find an anti-log button on your calculator, but all it really means is this. So all you need to plug into your calculator is 10 and then to the exponent. So your 10 to the x button on your calculator, it's for the x that you're going to put in negative, whatever that pH happens to be. Maybe it's 2.2 for the pH. So in the example that I have here, if the pH is 8.6, you can try this in your calculator. So you're going to get the 10 to the x button, and then you're going to put in a negative, and you're going to put in your number 8.6, and you're going to press enter, and then what you end up with is, so if we have the pH that's 8.6, the exponent for the concentration is going to be very close to that. It's going to be between 8 and 9, and that's exactly what this number is. 2.5 times 10 to the negative 9 is between 8 and 9, and the concentration are moles per liter. Don't forget to always include the units if there are units. There are no units for pH, but there are units for concentration, and that is moles per liter. Let's just take a look at two more problems here. So calculating the pH of this solution that we have. So this is a solution of nitric acid. Nitric acid, again, is a strong acid. So whatever you are told is the concentration of the acid, as long as it is a strong acid, that is also the hydronium ion concentration. Any calculations that you have to do for Science 30, they will be for strong acids. You won't have to do any for weak acids. So what is our equation? Directly from the data booklet, it's the negative log of the hydronium ion concentration. So what do we want to plug into this equation? Our concentration, 3 times 10 to the negative 4 moles per liter. This is what it looks like on your calculator screen when you actually put the numbers into your calculator. This is the way it will show up, and when you press enter, you end up with 3.5. So plug that in, make sure you can come up with this number here for your calculations. So the last one here is just going in the reverse direction. So calculating the hydronium ion concentration now when you have the pH. So this again is what is in your data booklet, 10 to the negative pH. Okay, you don't need to remember this equation. You don't need to remember this equation. It is right in your data booklet. So our pH, 9.5. So 10 to the negative 9.5 is what we're entering in. This is what it will look like on your calculator screen when you enter it. Press enter, and this is the number that you come up with. Again, always sort of double check. Take a look at the exponent here. The pH should be very close to that, and it is very close to that. Take a look at the pH, 9.5. The exponent should be very close to that, and it is very close to that. So always kind of double check, and if you're not really close, once again, then you probably did something incorrect with your calculations.